Legendrian submanifolds and Lagrangian cobordisms between them. Yeah, so first of all, I would like to thank Salman and organizers for the invitation. And of course, it's my great pleasure to be here. It's always nice to be in Golovko. My course will be about Legendrian submanifolds of a contact manifold of some special type, and also about Lagrangian cobordisms between them. So I'll try to move slowly, and I'll try to make it as accessible as possible. If you don't understand something, please ask me. So in order to talk about Legendrian submanifolds, first one needs to say a few words about contact manifolds and about contact structure. So, so the contact structure on a 2n+1 dimensional manifold is a maximally non-integrable hyperplane field. And to be honest, when I first saw this definition, I got a bit scared. There are some complicated words, but what they mean is essentially the following. So more formally, definition, one form on a 2n+1 manifold, and by one I mean smooth one form or differential one form. Let me write alpha, and let me fix some notation for the manifold. So my manifold will be M. Let me write it here. Okay, so in one form on a 2n+1 manifold, M is called contact. If this one form alpha batch d alpha to the nth power is different from 0. And the contact structure, so let me write like this. This one form, this contact one form, defines a contact structure Xi, and this contact structure is a kernel of a one form. Okay? So being maximally non-integrable hyperplane field simply means to be a kernel of some one form alpha, satisfying the property that alpha wedge d alpha to the nth power is different from 0.
Non-integrability condition reads in the following.
So basically whatever is said, right, if I have equal 0, then I will have so-called foliations, right? So this corresponds to the Frobenius theorem. And basically this condition, in a way, is just a consequence of the Frobenius theorem. As you see from the definition, the most important part is this distribution Xi, which is a contact structure, right? And a priori, so since this distribution is given as a kernel of one form, right, you can change one form and you will get the same type of distribution. So how you can change this one form? You can multiply it by the nowhere vanishing function. Okay? So if one, let's say like this, contact structure psi corresponds to many contact forms and in general, if you have one contact form alpha such that kernel of alpha is equal to psi, and you multiply this one form by the function f, so one takes f times alpha, where f is nowhere vanishing on M, then psi is also given as a kernel of F alpha. So F alpha is another contact form which defines psi. Okay? So in particular, the contact condition, so if you take F alpha, which d of F alpha to the nth wedge power, it can be seen to be F to the n plus 1 alpha, which d alpha to the nth power. Okay, so if this guy is non-zero, this contact condition is also satisfied. Okay, so now let's assume that we fix a contact form. So
what happens with the derivative term df? Something cancels?
yes, something cancels, and this is exercise. Exercise. Since it's a mini course, I need to give some exercises. So if we fix a contact form, so if you fix contact form alpha, then there is a special vector field, so-called Riemann vector field. Which corresponds to alpha. And let me denote it by R alpha. So this Riemann vector field is defined by two conditions. So condition number one says that alpha on R alpha is equal to 1. And second condition says that the inner product of R alpha and d alpha is equal to 0. Okay, so let's think a bit about these two conditions. So once again, contact structure is a distribution with a property that alpha on this distribution vanishes, right? So the first condition simply means that this Riemann vector field is everywhere transverse to the contact structure, right? So here we have some distribution psi, and here we have some Riemann vector field which is transverse to psi. The second condition, so I'll write it as a proposition, or lemma. So the second condition says that basically the flow of Riemann vector field preserves this contact form. So let me write it down formally. Let phi t be the flow generated by R alpha, then the pullback of alpha by phi t is equal to alpha for all t in R. So what's the proof of it? So the proof of it is basically the consequence of Cartan's formula. So we write d over dt of phi t star alpha. It's phi t star, then Lie derivative with respect to R alpha of alpha. And now we get phi t star d of I R alpha alpha plus I of R alpha and d alpha. So now this part, we know that alpha on R alpha is equal to 1. So d of 1 is equal to 0. So this is 1, hence this is 0. And the second condition tells us that the second summand is also 0. Right? So this is 0. So we can say that this is 0, and then we use that phi 0 is the identity map, right? Since we are talking about the flow, we start with the identity map. And we also know that phi 0 is the identity map.
Why did you get the first step?
What?
What's the first, could you explain the first step?
Oh,
First equality.
the first equality, here we use the first equality.
First, yes. Yeah.
That's just definition.
It's just a definition of the differentiation of the flow, yes. And here we use the Cartan formula. So we just write Lie derivative this way. So this part is a Cartan formula, and this is just a definition of the differentiation of the flow. So,
I have a question. So if we have can we always assume that we have one, like a contact form whenever we have a contact structure? Or
locally.
locally?
Yes. So if you have a contact structure, then we can say that there is always locally one form which defines it. Yes. So the existence of global form, it could be a separate question.
Yes.
So if one can define a global one form, but actually in this course, whatever we will consider, so right now I'm starting with some general definition, but we will take either the Euclidean space, and there will be a global contact form, or there will be so-called contactization of exact symplectic manifold, and there you will also have a global contact form.
We can conclude that it's odd-dimensional.
Excuse me?
And from this local description, we can conclude that the manifold is odd-dimensional.
It's a manifold of what dimension?
Odd-dimensional.
Of what dimension? Yes, yes, yes. Yeah, in particular, yes, yeah, true. Okay. So let's get to some examples. We saw some definition, abstract definition. Let's get to some examples. The most basic example, and it's also a canonical example. Why canonical, I'll explain in a moment, is a Euclidean space. So we just take odd-dimensional Euclidean space, R to the 2n plus 1. Here we take coordinates x sub 1, y sub 1, dot, 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 x sub n, y sub n, and z. And we take a contact form of type dz minus sum I from 1 to n of yi dxi. Okay? So in this particular situation, we can write down, let's do it. So let's write a contact structure for this one form. So the contact structure is given by, let me see, it's a vector space which is generated by d over dyi and also yi d over dz plus d over dxi. Okay, so we can write down explicitly what is our distribution of hyperplanes. So what is a Riemann vector field? Any guesses, since we have a graduate student workshop? Any brave hearts? What it could be? What solves these two equations?
Plug it in. Oh.
Yes. So I claim that d over dz, okay, R alpha d over dz is a Riemann vector field. Right, so basically so this is our alpha, and d alpha is the sum of dxi dyi, where I is from 1 to n, right? So alpha on R alpha will be what? So only dz part doesn't vanish, and dz over d on d over dz is 1. And also d alpha, if I just put inside d over dz, it vanishes because I don't have any dz components. So it's easy to see that this Rib vector field, that this vector field d over dz is a Rib vector field for this particular context structure. Also, some people write alpha standard here, and psi defined by this one form. People call it a psi standard. Why standard and why canonical? Once again, I'll explain in a moment. But it turns out that every contact manifold locally looks like a piece of an odd-dimensional Euclidean space with this particular contact structure. Okay, so let's take some more general example before we get to Darboux theorem. So slightly more general example is the example of the following form. So basically we take P times R with the form dz plus theta. So where here z is the coordinate on this R, and P d theta is an exact symplectic manifold. So since we are at the student workshop, graduate student workshop, I need to say that symplectic means that d theta is a 2 form. And which is closed, and it's easy to see that it's closed because it's d of something, so which is closed and non-degenerate. So sometimes called symplectic form.
What's theta?
So, sorry, I'll write it. So theta is a 1 form. Okay. So we take example of type P times R. So on R we have z coordinate, and we have theta, it's a 1 form on P. And we have a property that P d theta is exact symplectic manifold. So symplectic means that we have a manifold with so-called symplectic form. And symplectic form, it's a 2 form, which is closed and non-degenerate. This exactness means that our symplectic form can be written as a D of something, right? D of some 1 form. So, I don't know, we can fix dimension if you want to, but let's say this P is 2n dimensional. So being symplectic means that this manifold is even dimensional. And the Rib vector field in this particular situation once again, any brave hearts? Excuse me? Sorry? It's again, it's the same thing, right? It's d over dz. Right, so this is the right answer. Rib vector field, let me write this guy once again as alpha. Rib vector field R alpha is given by d over dz. And this comes by the same logic. Great. Now, clearly, this is a generalization of our Euclidean example because basically P we could assume that P is R to the 2n, and our symplectic for our one form is pretty much this minus sum of I from 1 to n of yi dxi. You can say, well, are there any other examples? And the answer is yes. So in particular, one can take one jet space of arbitrary manifold, which is a cotangent bundle of the manifold times R. And one jet space is exactly of that form. So if on M we have a Q coordinate, right? And on the fiber we have P coordinate, then and on R we have Z coordinate, then we have a one form dz minus sum of PDQ. Okay, so I didn't write indices, but somehow we pair each type of P and each type of Q. Okay, so this is another example of the guy of this form that appear naturally. Okay, and the third example, you can say, well, maybe everything that we have has a Rib vector field with the property that there are no closed Rib orbits, right? So in this particular situation, you see that Rib orbits, I mean, the integral trajectories of this Rib vector field, they are not closed. I mean, it's just d over dz, right? So, and I would say no. There are some examples where it doesn't work this way. So
We can replace R by S1.
that's what I'll write.
Oh, okay. Then the dz is the...
Yeah, I'll write something slightly more complicated, actually. So I'll write example, which is a sphere, odd-dimensional sphere. So S to the 2n plus 1, which sits inside R to the 2n plus 2. And let's say here we have coordinates x sub 1, y sub 1, x sub n, x sub n plus 1, y sub n plus 1. Okay. And the contact form, so alpha in this particular situation, it's a sum of xi dy minus yi dxi I from 1 to n plus 1 restricted to s to the 2n plus 1. So basically we take alpha leaving in R to the 2n plus 2, we restrict it to our sphere, and this is a contact form. Exercise, try to compute Rib vector field in this particular situation. So exercise, compute Rib vector field.
Can I guess? No, I'm just curious.
You can.
Is it like J times the outward normal vector field? Where J
What is J?
Like the standard almost complex structure.
You can even take complex structure in this particular case because we are talking about C to the, I mean, complex structure.
Well,
yeah.
Now we collect these exams, these assignments.
Sorry?
We are going to check these assignments, collect these homeworks.
Yeah, well, it is, yeah, they're just exercises. So, okay, now why did I say that this example is a standard? And what is this statement about being canonical? So let me keep this example, since I'll talk about it. Sorry, I'll try to make it not very dusty. So there is a theorem of Darby, which basically says that there is no locally interesting contact topology. So what it says precisely is that, so let M psi, let's say dimension is 2n plus 1, be a contact manifold and you say that any point P in M has a neighborhood U is a diffeomorphism phi from U to some V which lives in R to the 2n plus 1 with a standard contact form such that phi of P is equal to 0 and let me write that this psi here is given as a kernel of some alpha. So and psi pullback of alpha standard is equal to alpha. So this means that every contact manifold locally looks like a part of the Euclidean space. Okay? And from this perspective, studying contact manifolds locally is the same thing as studying Euclidean space locally. And as far as questions about Euclidean space are answered, the questions about structure, local structure of the contact manifold are answered. So from this perspective, one can say, well, maybe contact structures are not so interesting. It's actually not true. So they're interesting because of some global invariance and global properties. So somehow the way to talk interestingly about them is really to study some global invariance and global properties of contact structures. So, so once again, I used to be a student of Kohonda. Kohonda is Japanese, so I usually formulate the most important parts as zens. So let me write zen. So the zen says that the interesting contact invariance and contact topology, or contact topology in general, are global. Interesting contact invariance are global invariance. Or global topology. Okay, so here we are. Now we can get to the subject of this mini course. So let me talk about Legendrian submanifolds. You know where they could live. So definition. A Legendrian submanifold of a contact manifold M psi, let's say M is of dimension 2n plus 1, is a submanifold of dimension m such that it's everywhere tangent to the contact structure. Let me give some name for this submanifold. Let me write lambda for it. Okay, so side Z, the tangent space to lambda at the point X is a part of the compact structure psi, and this is true for every X in lambda. Okay. Now we will consider Legendrian submanifolds up to Legendrian isotopy. So let me define that. Definition. So let lambda 0 and lambda 1 be two Legendrian submanifolds of a contact manifold M2n plus 1 Xi. You say that lambda 0 is Legendrian isotopic to lambda 1 if there is a map F from 0, 1, okay, let me write from lambda times 0, 1 to M side Z. So 1, F restricted to lambda times T is an embedding for all T in 0, 1 to F on lambda times T is Legendrian for all T in 0, 1. And 3, of course, F on lambda times T is lambda T for the ends. So basically, we have a one parametric family of embedded Legendrian submanifolds which start at lambda 0 and end at lambda 1. Okay? So this is a Legendrian isotopy. Now, before talking about examples, let me also describe two natural projections that we will use. So there are two natural projections. There are two natural projections. So I'll define them in the most general settings, and then we will see them in the most basic settings. So first projection is a front projection, And sometimes one can define some version related to open book, but let me not do this. Let me consider so the most general case for me will be the case of one jet space. So basically one can take this J1 of M, which is once again a cotangent bundle of M times R, where here we have, so on M we have Q coordinate, on the fiber we have P coordinate, on R we have Z coordinate. And basically we take a map, so our front projection will be a map from this one jet space to M times R, where you take QPZ and we map it to QZ. Okay? And another thing is so-called Lagrangian projection. Lagrangian projection. I'll denote it by pi L. And I will define it in the case of, once again, P times R is dz plus theta, this contactization of exact symplectic manifold. So it's a map from P times R, where on R we have Z coordinate and on P we have X coordinate. And we map it to P, where we take X and Z, and we just forget about Z. Okay? So there are these two projections. Why it's called Lagrangian? Because basically you remember that this manifold P d theta is exact symplectic. Namely, this is a symplectic form. It's a 2 form which is closed and non-degenerate. And it's called Lagrangian because whenever I take lambda in P times R, and this lambda is Legendrian, so it's Legendrian, I have that pi L of lambda is so-called Lagrangian in P d theta. So Lagrangian means that this d theta restricted on pi L lambda is equal to 0, right? It vanishes.
Is that true? You can always write this like manifolds as a P times R, 2n plus 1 dimensional manifolds. P times R.
I can write always what?
We can write always like P times R.
There are some contact manifolds that are not of this form.
Then for such manifolds you cannot do like
Then you cannot do,
projections?
yeah, as I said, so I describe the most, yes. I describe the most general versions of this projection. So Lagrangian projection most generally is defined when I have a contact manifold of this type. And front projection is most generally defined if I have something like a one jet space. So I need to have some information about the manifold and about this extra contactization direction, and the rest it could be either part of Euclidean space or it could be fiber of some bundle, like cotangent bundle in this case, or things like that.
Is it obvious so that lambda is Legendrian, P plus R,
Yes?
and the theta vanishes on the image of lambda?
Yes, it more or less follows from being Legendrian, right? So Legendrian means to be of maximal dimension and to be tangent to the contact structure. So basically, the projection will be always isotropic. You can write it down. Yes, and maximality will also follow. It will be so the projection will be immersed n-dimensional submanifold, and yeah. The fact that it's tangent to the contact structure will correspond to the, so basically this alpha, what we can say, so in particular you can say that this d alpha, when I restrict to my contact structure is a symplectic form. I can say that, right? And in particular this will reflect this will correspond to this fact that the projection will be Lagrangian. Okay, makes sense. Okay, so these are two projections. Now let's get out of this abstract theory to something concrete. So we all like knots, we all like pictures, we all like diagrams. And as you see, the simplest example of a contact manifold is just three-dimensional Euclidean space. We can imagine it, we can write down many things there. And so for a while, our friend, our contact manifold to consider will be R3 with the form dz minus y dx. Okay? It's a nice contact manifold. And one can consider Legendrian submanifolds there. And we will consider only closed Legendrian submanifolds, namely compact Legendrian submanifolds without boundary. What's a one-dimensional closed manifold? Do we know many closed one-dimensional manifolds? Or one-dimensional? Oh. Yeah, I'm asking students. S1, great. So in the case of R3 with this contact form, we are talking about S1s inside, namely about Legendrian knots, right? So in the case of R3, we will talk about Legendrian knots. Okay, so let's discuss Legendrian knots inside. So for R3, of course, there are these two projections. Front projection, in this case, is just a map from R3 to R2, where you forget about y-coordinate. And Lagrangian projection, it's a map from R3 to R2, where you forget about z-coordinate. Okay? And let's try to see what are the potential projections of Legendrian knots in R3. So what are the front projection? What are the Lagrangian projection? So what type of restrictions do we get from this contact condition? Because basically we are studying Legendrian knots. It's like studying smooth knots with some extra condition. Yes?
So, I mean, I'm just have a question about your notation.
Yes?
In the one-jet bundle, is P the base?
So Q is a coordinate on M and P is a coordinate on the fiber.
Okay.
Yes.
Close?
Because we like closed submanifolds.
Okay, but you can always define any projection.
Well,
any kind of manifold.
one can consider not just closed, but I mean, sometimes they are more difficult to study. So, and I mean, usually, you know, yeah. Okay, so let me remove this stuff. So what's the question to consider? What are potential pi f and pi, let's say pi f of lambda and pi l of lambda for lambda Legendrian knot in R3. Okay. So let's start with the front projection. So first front. So take pi f of lambda, and let me also, since I don't have a okay.
we have almost 15 minutes.
Okay, great. Okay, thanks a lot. I didn't take a watch. So, what's the front projection of lambda? So basically, once again, we have a map from S1 to R3, and let's say our map looks like theta goes to x theta, y theta, and z theta. We write it down in terms of coordinates. Then the contact condition, so from the contact condition, we have that z dot of theta minus y of theta x theta is equal to x dot of theta is equal to 0. And hence, you can write down y theta as a z dot of theta over x dot of theta. So the way to say is that whenever we take xz projection, right, we can actually recover y coordinate from the slope of whatever we have in the projection, right? So this z over x slope. Okay, so front projection, we can say that front projection of a Legendrian knot completely recovers Legendrian knot. And also we can say that for a generic Legendrian knot, front projection is embedded everywhere but in the finite number of transverse points and cubic cusps. And because of the contact condition and its tangent line is defined at cusps, so let me draw some examples of Legendrian knots in the front projection. Yeah, also from the contact condition we can say that there are no vertical tangencies. Vertical tangencies at of front projection. So the easiest example of a Legendrian knot is a unknot, and it can be written this way. So this is these cusps. Okay. Now let me draw a trefoil. So this is a trefoil. If I'm not mistaken, it's left-handed.
Right-handed.
What's that?
Right-handed.
It's right-handed, yeah. Trefoil, yeah. And another thing that I need to say is that, so if you look, so maybe another thing, if you look at the knot from y equals minus infinity, maybe whatever I say is a bit informal, but so whenever you looked to the knot from y equals minus infinity, so we will see that upper strand, so let's say like this, strand with negative slope is above the strand with positive slope. So what I mean is that at each crossing, the strand with a negative slope will be over strand, and the strand with a positive slope will be under strand. Okay? So whenever you have a diagram with this type of behavior, right? So at each crossing and also cusps, you see the diagram of the Legendrian submanifold. It's a front diagram of a Legendrian submanifold. Actually, there is a theorem or fact saying that every plane curve with isolated cusps and transverse double points. Let me put comma instead of and. So transverse double points. No vertical tangencies. Is a front projection of a unique Legendrian knot. So whenever you write something like this, you're sure that you're drawing some Legendrian knot. Now you can ask, well, is there any relation between these Legendrian knots and, just knots? And can this relation be proven, let's say, with a front projection? So before going to the Lagrangian projection, let me write the following statement and prove it. So it turns out that there is a C0 approximation of a...
Non-vertical tangencies exactly?
Excuse me?
Non-vertical.
We don't have vertical tangencies because y, right, is a slope, dz over dx, and y cannot be infinite, right? So we consider compact Lagrangian. Yes. So this basically comes from the contact condition. Okay. So there is this approximation theorem. Approximation. Theorem. So it says that every arc in a contact three manifold let's say m psi can be C0 approximated by a Legendrian arc which is smoothly isotopic smoothly isotopic to the original one relative endpoints. So what's the proof? So I'll write proof okay, the proof is the following basically. So first of all, we can consider everything inside R3 because of Darboux theorem, right? So if you have something Legendrian, we can always some arc, we can, if you have some Legendrian arc, or if you have some smooth arc, we can always put it put it inside some Darboux ball, right? And we can consider just the case of R3, and we can basically approximate this arc by the following zigzag picture. Something like this. So it turns out that this type of picture is C0 close. So whenever you write it down, you can actually see that it's C0 close. So this way you can make y coordinate to be close to the y coordinate on the original arc. Unfortunately, this type of procedure, even though it provides you some approximation, it's not very nice. In a way that usually people don't use it if one wants to do some sort of like some approximation of a smooth knot by the Legendrian knot. The way to proceed, if you take is, so let me draw it here. So if one wants to get, if one starts with a smooth knot or smooth arc, and one wants to get a Legendrian arc in the same smooth homotopy class or smooth isotopy class, one can also do the following. So like local modifications. That allow to get from smooth knot, Legendrian knot in the same smooth isotopy class. So basically what you can do, instead of doing these zigzags, what you can do, you can locally do this type of change. So each vertical tangency can be replaced with a right cusp. So each vertical tangency, so curly this way, can be also replaced with a left cusp. Then, whenever you have a crossing of the right type, of course you don't do anything. But if you have a crossing of an opposite type, right, so if you have something like this, then there are two scenarios. You can either do this type of local modification, or Sorry. Yeah. Or you can do this type of local modification. So basically, if you have a smooth knot and you have a diagram of a smooth knot, you can make it a diagram of a Legendrian knot in the same smooth isotopy class by doing this type of modifications. And adding this type of zigzag that we used in the approximation theorem is actually harmful. Why it's harmful, I'll explain later in the course, but just to provide some idea, it turns out that if we add these zigzags, we'll actually kill all interesting invariants of the knot. So adding this type of zigzag corresponds to so-called stabilization of a Legendrian submanifold of a Legendrian knot, and this will kill all holomorphic invariants. So this type of procedure is better than that one. Even though if you do this type of procedure, you cannot control y-coordinate, and it can be very different from the y-coordinate of the original knot, so you don't have C0 approximation, but you still stay in the same smooth isotopy class. Okay. How much time?
Time, like -5 minutes.
Oh, okay. Yeah. Sorry for being late. I'll continue next time. Maybe I'll try to be a bit faster. But thanks a lot.